Hey there, welcome. So what I'm going to be doing today is going over a few example problems using the tools of kinematics that I introduced in the last lecture. So I want you to have just some examples of not only the graphs, how to look at those, but also and how to think about those, but also some problems that I've just lifted from the textbook. Um, so we'll go over a number of these. All right, so we're gonna go ahead and share the screen. All right, so first thing I want to do is just start with a basic position time graph. Now, I want to I'll just paste this into the notes here. Sure that works. Okay. All right, cool. So there's a basic position time graph. Now, you might be asked to do a number of different things with this. So first thing you might be asked to do is like describe the motion. Oops, change this. So describe the, actually, I'll do this in bold and then, so describe the motion. Now the idea here is you want to be able to sort of, you might not know what object this is, but let's just say that this is, a person walking. What you want to be able to do is you want to be able to say certain things about how the person was moving, and then maybe something about the rate, something like that. So what I would say is, it looks like starting. So this is something that you want to be able to do. Say the starting point. Now, in order to the starting point, what you're going to want is you're going to want the position at time t equals 0. Now, notice it doesn't start at 0. It starts a little higher than that. So I would say starting at a position of 3 meters, then what happens? We just say the object moves we could say to the right. I'm going to say in the positive direction, because we notice the position is increasing. So whichever direction that we've defined as positive, that's which direction it's going. Now what we can say about this, we can say that this is almost a straight line. Now what that means is that the position is changing roughly the same for each time interval. Now you can tell it's not exactly the same, but what we can say is that in the first 10 seconds it increases about 2 meters. In the next one, in the next 10 seconds, about 3 meters. So I would say at around 2 to 3 meters each second. Okay. And that's basically how you would describe this one. Now, another thing you might have to do is you might have to look at you might be told to sketch the velocity time graph. Now, it turns out this is not too bad because this one has a basically constant velocity. So we said that the velocity was around 2 to 3. So I would just go 1, 2, 3 for the velocity. So 1, 2, 3. And then we can do, I'll go by 20. So 20, 40, 60, and then 80. And it only goes out to about 70. But the idea here is that the velocity is roughly constant. Now, how we would draw that, I'll do this in green since they tend to draw velocity graphs in green. We just draw that as horizontal. Okay. Now, as a reminder, basically what we're doing is we're finding roughly what this slope is. And so you could pick any 2 points on this graph. It might be easiest to take the first one and the last one. So this one was 0, 5, or no, not 5, 3, I believe I said. And then the last one looks like 70. Oh, this is not each second. I made a mistake. It's each 10 seconds. So 10 seconds. Be careful with that. So now this is where that comes in. It would actually only be 0.1, 0.2, and 0.3 if we have our velocity in meters per second. So in between 0.2 and 0.3 meters per second is what's going on. Now, for this other point, it looks like I'm going to say we're at about 18. So that looks pretty close. So we want to find the slope. Remember, the velocity equals the slope. So we do the rise over the run. And the rise would be 18 minus 3, and the run would be 70 minus 0. And we'd end up with 15 over 70. And I think that ends up as being 5 over 14. I think that's right. No. 3 over 14. Yeah, 3 over 14. Okay. And 3 over 14 you could convert to a decimal, but whatever. It's somewhere between 0.2 and 0.3. So that's basically what we'd be looking at there. Now, the acceleration, another thing we might be asked to do is find the acceleration versus time graph. And basically what this would look like. As a reminder, you can think about this a couple of different ways. First of all, the speed isn't really increasing. It's going at more or less a constant rate. The position is more or less increasing at a constant rate each time. So the speed isn't changing. The other way you can think about it is you can look at the slope of the line you just drew. Now this horizontal line, so I'll do this in blue. A equals the slope of this graph. And that's just m is approximately equal to 0. So all you do there is you just do the acceleration at a constant 0. So it'd be 0, and then you could, run that out to 70, whatever. But that's just sketching it, and so you can kind of get a sense of what that looks like. So this is kind of the thing that you would need to be able to do with these position versus time graphs. Now I'm not gonna go. I want to show a slightly different one. So here, let's see. To paste this. Oops. And there we go. Okay, so what we've got here is now we've got a position time graph where the position it's definitely increasing, but it's going up each time. So in the first 5 seconds, it looks like it goes from, I'm going to say about 200 to 500. So basically, we could say something like this. We were asked to describe it. We could say starting at a position of 300. The object moves to the right. Now, you could say this a number of different ways. Moved about 200 in the first 5 seconds. So 5 seconds, plus 200 meters, 10 seconds. So the next 5 well, we'll say you have an increase of 200 meters. Now in the next 5 seconds, so next 5. So going from 5 seconds to 10 seconds is the way to think about that. You go from about 500 to about 800. So you have an increase of around 300 meters. So increase of 300 meters. So the way I would put this, now we don't need to calculate this all right now, but basically what's going on here is it's at an increasing rate. Okay. Now, part of what we're going to do when we find the velocity is we're going to find that rate. But if we're just asked to describe it, that's fine. Okay. Now, if we were asked to find the velocity versus time graph, basically what I would do, I would find the slopes between each one of these 2 points and then kind of just use the average. So what I would do is so between the first one, so the first velocity point, I'll just call this V1. It would be, the rise would be 500 minus 300, and the run would be 5 minus 0, like that. So that's between these 2 points right here. And from there we can, it ends up being 200 over 5, which is 40. Now, the question is, so we have a velocity of 40. Now, the question is, where do you put that in time? Well, what I would do is I would put it at, 2.5. And then I'm going to increase this. Basically, what I would put it in between the 2 times that we calculated. Now it's kind of optional if you do this, but I'm gonna just go up by 5s from there. So 12.5, 17.5, 22.5, and then 27.5, and that should be enough. So basically, we're calculating the velocity in between all these 2 points. So our first one would be right there. I'll do this one in green. All right. Now the second velocity, v2, we can calculate this. It would be, looks like no, I said 800 minus 500 over 10 minus 5. So it's going to end up being 300 over 5, which will be 60. So 20 and then 60 right there. So we would go like so. Okay. And then V3. Oops. V3 would be, looks like the 15. What do we got there? Let's say about 12. I think that's about right. So it's about 1200 minus 800 over 15 minus 10, which would end up being 400 over 5, which would be 80. Okay, so what you can see, you can kind of get what's going on here. And you can go through and do this. But what you can see is that your velocity is each 5 seconds, your velocity is basically increasing by 20. So if we do the next one, it's a little difficult to tell, but I don't know. Yeah, I think that one, it might have misread that a little bit, but that one is probably in any event, you could make an estimate and yeah, well, wait a minute. Oh, I see. I need to go to 20. Is that 15? So So that one looks like it's only about 16, which would give us 16. I suppose we could fudge that to 17. But it's a little bit difficult to tell on this scale. But in any event, you get the idea what's going on. So I'll only do the velocity for the first three. Looks like it started with some rate here. Looks like it would have started about there. But your velocity curve would look basically like that. Now, if we wanted to do the acceleration curve, the acceleration versus time is just going to be the slope of this thing, okay? So assuming this is roughly straight, which is it's not a bad assumption, we can then go roughly linear. We can then find just the slope of the acceleration curve right there. And from that, what we get is we would get so the slope would then be so we have 60 minus 40 for the rise, just using those first 2 points, over 7.5 minus 2.5, which would be 20 over 5, which would be 4. So basically, the acceleration is always going to be 4 because the slope is constant for this one. So switching to blue, we go to 4, and we just have a horizontal line there at 4 meters per second squared. So that kind of gives you a sense of what these different things look like. Now, the book provided an example roughly of what the velocity time curve looked like. So I wanted to just compare with that with what we got here. So the book's example looks like that. And you can see that it's basically linear. Now its scale is a little bit better than mine, but you can see it starts a little below the 20. I thought it would start at 20. But you can see it's just kind of going up piece by piece. Now, one of the things they did here is they marked the points at the different times. Now, this is a little bit different because we defined some averages there. Now, what you could do is you could pick the points slightly differently, such that you could calculate it at the times of interest. So, the fact that we have this initial graph, if we wanted to know it at 5 seconds, what we could do is we could take this point and this point, and use that to calculate our slope, that would be a perfectly reasonable thing to do as well. So that's just something to keep in mind with that. So I think, yeah, there were two more that I wanted to look at. Now, this next one is a little bit tricky. It's actually a lot tricky. But it's worth taking a look at just to see kind of what's going on with it. Okay. Now, when you think about this, basically what's going on here is you might be asked, first of all, could you describe what's going on with this thing? Okay. Could you describe what the motion is? And basically what the motion is it moves in the negative direction. So basically this region right here is a negative direction, is a negative direction of motion. This one right here is in the positive direction. And then it switches directions and goes back in the negative. So that's negative. And then finally, it goes back in the positive. Now, what this means, if it's this thing is constantly switching directions. Now, on the whole, it's moving in the positive direction because it's moving more positive than negative. But if you notice from A to B, its position gets smaller. Then from B to C, its position gets smaller. Now, once you get to C, that is basically a stop. Once you get to E, that is another stop. And once you get to G, that is another stop. Now, that's when this thing switches directions. Now, it's important to know that in the negative direction, if it's moving in the negative direction, what this means that the velocity is less than zero. Okay? The velocity is greater than zero right here. And then the velocity is less than zero right there. And the velocity is greater than zero right there. And you can kind of see that you could approximate a slope like between A and B, and that would have a negative slope. You could approximate a slope between B and C. That would have a negative slope. Between C and D, it would have a positive slope. Between D and E, so on and so forth. So that's how you can know kind of what the velocity looks like. Now, if you wanted to know something about the acceleration, it's a little bit more difficult to tell from this kind of graph. What you'd really want to do is you'd want to go and plot the actual velocities. Since we don't have any numbers, we can't really do that. But what we could do is we could say, okay, if we wanted to plot like an approximate velocity versus time graph, we actually need to let the velocity go negative in this case. But like we said, it started in the negative, so the velocity is negative. And then the velocity, it got less and less negative until it got to point C where a stop occurred. Now, the point there is that when the thing is stopped, so that's at points C, D, and G, that means the velocity is zero. So this is something that's very useful to remember. If you're told in the problem that the thing is stopped or that it's at rest, what that's saying is that velocity is equal to zero. So this is something we can take advantage of. We can mark our stops on the time axis because at those times, at times C, D, and G, the thing was stopped. So we would do, we'd have D there and then G there. Now, we knew the velocity is negative before C. It's positive after C, but it's got to go back to negative at D, and then it's got to go back to positive at G, at which point it kind of just stays positive. Now, it does actually look like it's possibly changing direction. So what might be happening is you might have something like that, and then it stops a little bit before it can get back to zero. But that's just a rough sketch of what this thing would look like. Now, from there, what you could do is you can make a rough sketch of the acceleration, roughly what the acceleration looks like. So if I wanted to do acceleration versus time, acceleration can also go negative, by the way. Now, as a reminder, what you have here is you have the slope of this graph is your acceleration. And again, this is just an approximation. But notice here we have a roughly positive slope. So I would take something like that for that first segment. There we have a roughly negative slope. So I would just drop it down to like a negative horizontal line. There we have a roughly positive slope. I'd bring it back up. And then there, very small negative slope like so. Now, this is what acceleration graphs look like a lot. They look like you get these abrupt changes, so they look kind of like square waves. And you can connect the vertical like I did. You don't necessarily need to. I kind of like to. It makes me feel like I'm done with the problem, but you don't necessarily need to. Okay. So that's what's going on with acceleration. Okay. So that's one of the things I wanted to show you. Now, last graph I wanted to introduce is it's a velocity time graph. And it's helpful again to sort of interpret what's going on. Whoops, let's put it. Okay. All right. So interpreting velocity time graphs is a little bit different than position time graphs. So what is important to know here is that here not only is the velocity positive, but it's also increasing. So velocity is positive and increasing. Now, as a reminder, what that means is that your acceleration is greater than 0. And you can kind of see that. You've got a slope here, right there. Okay, so that's that one. And I'll switch colors. Switch to green. There, velocity is positive, so it's still going in the same direction. That being the positive direction. But what's going on here is it's no longer increasing. I'll say, and it's now constant. Okay. So what that means is it means that your acceleration equals 0. Okay. And then finally, if we look at this one has your velocity is still positive, but it's decreasing to 0. But is decreasing to 0. All right. So that's basically what's going on in this situation. So what we have here, we'd have acceleration is less than 0. Now, if we wanted to do an acceleration versus time graph, wouldn't be that bad. So acceleration and then time. Now, what I can do, I've kind of got it. A lot of times it's helpful to draw them right underneath it, and then you can mark the corresponding spots on the graph. Now, initially we had this positive constant acceleration. It looks like 3, and then the velocity goes up 1, 2, 3, 4, 5, 6, 7. So about 7 over 3. So about 2 1/3. So 1, 2, 3. It would be right about there. Okay. And then we have an acceleration of 0. Now that's just a horizontal line at an acceleration of 0. So it looks like that. And then it looks like it takes us about 5 seconds to drop 7. So it'll be 7 over 5, which is a bit less than -2. So we'd have something that looks like this for the end. Okay, so that is basically what your acceleration versus time graph would look like. Now, there is a way to construct a position time graph for this. As it turns out, it needs some calculus, which I'm not going to go into. So that is neither here nor there. But what you can do, I'm going to copy this one more time, is you can get displacement from this thing. So displacement from this graph. All right, now as a reminder, delta x, this is just the area under the velocity time graph. Okay, now how are we going to find that? Well, this turns out to be a trapezoid. And so basically I'll shade it in. It would be this area right in here. All right. Now it's a little bit tricky if your velocity goes negative because then you have some negative area as well that you need to subtract. But this one is fine. The velocity is not going negative, so we don't need to worry about that. Now the bottom base, it looks like so base 1 is the bottom equals around 23 seconds. Base 2 looks like it goes from, what do we say, from 3 to, I don't know, about 19 maybe? I think it's about 19. So 3 to 19, base 2 would be yeah, base 2 would be 19. Actually, no, sorry. It would not be 19. It would be 19 minus 3, which would be 16. Just to make the calculations a little bit easier, I'm going to say it's 18. So it's 18 minus 3, which would be 15. Sorry. Yeah, 18 minus 3. So basically this length right here, that would be 18, that would be 3. So the entire length is 15. So that would be 15 seconds right there. And then the height is 7. So as a reminder, the area of a trapezoid is base 1 plus base 2, 1/2 times b1 plus b2 times height. If it helps, you can actually convert that into two triangles and a rectangle. If you need help getting it that way. But basically it's going to be 1/2 times 23 plus 15 times 7. Okay. 2, 3, 4, 5, 6. Yeah. Okay. So 23 plus 15 is 38 times 1/2 is 19. 7 times 19 is 133. So your area would be 133. So that means you get about 133 meters there is what's going on. Now, as a reminder, your height was 7 meters per second. So if you're multiplying meters per second times seconds, then you do get meters. So your units end up working out there. Okay. Now, in terms of what situation this is actually describing, this is actually an elevator, what an elevator is doing. So it starts off with a velocity of 0. It accelerates up to a constant velocity, carries you up to the top, and then slows down to a velocity of 0. So, you go up 133 meters. That's, your velocity time curve might look something like this. Okay. So that's what's going on there. All right. So what I wanted to do next is I had a few questions that I wanted to go over just in terms of how we'd use the kinematics equations. Probably just go over all of these. Why not? You got time in this recording. Okay, so the first one looks like this. All right, a bullet is accelerated from the firing chamber to the end of a barrel at an average rate of 6.2 times 10 to the 5th meters squared. For 8.10 times 10 to the negative 4 seconds. What is its muzzle velocity? That is its final velocity. Okay, so I want to do this in particular so you guys can see the algorithmic approach that I'm going to use for this. Now, as a reminder, I said there are going to be 5 basic quantities that you can use. I like to write down the symbol for those from the get-go. So I will say delta x. And we don't know what delta x is. That would be, like in this situation, that would be from the firing chamber to the end of the barrel. Okay, so we don't know what that is. What is V initial? Now, here is the thing. This isn't actually told to us, but it's something we can infer, okay? And it's important to be able to do this in physics problems. Is the bullet initially moving? It's not, okay? When you fire a gun, the bullet is not initially moving, so your initial velocity would be 0. Your final velocity, well, we don't have that, but turns out that is what we want, okay? And then we do know our change in time, the time that this took. Again, sometimes people will just do t, but that's 8.10 times 10 to the negative 4th. And then finally, we do know our acceleration. That is 6.20 times 10 to the fifth. Now, the point here is that what we want is we want an equation that so this is pretty typical. Usually in these problems, you'll be given or be able to figure out 3 of the kinematics quantities, and you'll need to solve for the 4th one. What you want to do typically is you want to use the equation that has 3 of the things you have and 1 of the things you don't have, and the thing you want. Okay. So there is this time independent equation, or sorry, not the time independent, the displacement acceleration equation, which has initial velocity, time, and acceleration. We could use that to find displacement, but we're not asked for that. We're asked for muzzle velocity. Okay. So what I would do, turns out the equation I would use, I think this is the 4th one I gave you. I would use the V final squared equals V initial squared, and I might have put the V initial squared after. It doesn't matter because it's just plus 2a delta x. And then from there, we just plug in and solve for it, okay? We don't know the V final, so we'll leave that alone. V initial, which is just 0 squared, because V initial. And then 2 times 6.20 times 10 to the 5th times 8.1 times 10 to the negative 4th. Okay, so basically what this is going to end up being, we could solve for V squared right now if we wanted to. I do encourage you to keep significant figures, even perhaps keep more than you need to in intermediate calculations, because you want to do your rounding at the end. Doing intermediate rounding can lead to problems. So 6.02, 62 times 8, whoops, times 8.1 times 2. And that would be 1004.4. Now notice, that's too many sig figs, okay? I'm only allowed to use 3 sig figs, but I'm going to keep it until the end. And at that point, I will use 3 sig figs. How do I know I'm allowed to use 3 sig figs? Well, these two, oh, it's 8.10, sorry. And I wrote that. But these two both have 3 sig figs. Okay. So then what we want to do is we want to take a square root. And when we do that, that's going to give us V final will be equal to 31, and then it's 0.692. I'm going to round here to 3 sig figs, 31.7 meters per second. That seems a little slow. Did I? Seems a little slow for a bullet. Just curious. Let me just make sure that I did this calculation. 22 e to the 5th times 8.1 e to the negative 4. Yeah, looks fine. Times 2, and then take the square root. Yeah. Okay, so that is basically what this would be. Now, I checked this. 31.7 meters per second does seem actually quite slow for a bullet, but maybe this is like a pellet gun or something. So maybe that's what's going on there. But in any event, hopefully you got this. I use delta x instead of delta t. So this is actually a good demonstration. I used the wrong equation here, because I was using delta x instead of delta t. I was not given delta x. This equation would have been valid if it only had this much distance to accelerate. That is definitely not true. It had more time. So the equation I actually want is it's just going to be the velocity equation. It's going to be V final equals A delta T plus V initial. And when we do that, this is going to be V final equals 8.10 times 10 to the negative 4th times 6.20 times 10 to the 5th. And so that would just be, oops, Um, just be, you'd get a V final, and this seems much more reasonable, 502.2 meters per second. Okay, I think this was the third equation I gave you. So yeah, in the recording, you get to see me make a mistake. And the reason I caught it, it's a good lesson for you. The reason I caught it is because I looked at that and I thought, 30 meters per second does not seem very fast. Um, it's not, it's too, this is not perfect. But if you ballpark, just if you just want to get in the ballpark, just so you can compare it to things you might be more familiar with, approximately double it's a little more than double, but approximately double the meters per second will give you miles per hour. Just FYI. So something going at 30 meters per second is only going 60 miles per hour. That is really slow for a bullet. Okay. A bullet should be going a lot faster than this, and over 1,000 miles per hour is reasonable for a bullet. Okay. So that's just something that's the way you can kind of do a reality check with these ones. Worth knowing. All right. We'll go on to this one. Okay, next one I wanted to do was 24 in the book. It says, while entering a new freeway, a car accelerates from a rest at a rate of 2.4 meters per second squared for 12 seconds. Okay, we've been given a couple of things. So I'm just going to write those down from the get-go. A equals 2.40 meters per second squared. Delta T equals 12.0 seconds. So and then list the knowns in this problem. Okay. Well, I'm already kind of doing that. The other thing I know, always ask if you know the initial or the final velocity. In this case, we know the initial. It's 0 meters per second. Now, one thing that some people will make a mistake is, and we'll see this in one of the free fall problems, I believe, is that something will ask, a problem will ask what speed something hits the ground with. People will assume that because it hit the ground, it stopped. Now, that's not what the problem's asking. The problem asks, how fast did it hit the ground with? So if you were there and you were hit by this falling object, it doesn't want to know how fast it's going after it's hit you and stopped. It wants to know how fast it was going right when it hit you. So be careful with making that assumption. But typically when it says it starts from rest, that's a good indication that its initial velocity is 0. The other thing it could do is it could slow down to rest, in which case, if it slowed down to rest, like it was coming to coming to a rest under friction or something, then you would use a final velocity equals 0. We could draw a sketch of the situation. Basically, what I would do is I would say, okay, we could just do X versus T. Now I guess I'll do V versus T first, and it starts from 0, and then each second, 1, 2, 3, we could go all the way up to 12. It's basically going up by 2.4. So we'll do 2, 4, 6, going up by a little bit more than 2 each time. So it would look like this. That's fine for a sketch of the situation. Being able to connect the sketch to the problem it can be useful, particularly if you're asked to find something else. But in this case, I think the equations will mostly get us where we need to be. Now, listing the unknowns, what we're asked to do is we're asked how far does the car travel. So delta X is what we want to know. Now, another unknown we don't have, and I like writing this down and just acknowledging it, we don't know how fast the car was going. Okay. Now, it turns out in part D, we are asked to find that. So we're going to need to find that as well. Okay. But for part C, what we'll do is we'll use the equation that has acceleration, time, initial velocity, and delta X. And what that is, that's delta X equals 1 half a delta t squared plus v naught delta t. Now plugging in, you might need to do some algebra to solve for some of these. In this case, we haven't so far. But plugging in, what we get here is we get just 1 half times 2.40 times 12 squared plus 0 times 12. Okay, so basically what this is going to be, 144, that's 12 squared times 1.2. And that's going to give me delta x will be 172.8. Now it's important, I only get 3 sig figs. So what I would do, 172.8, you round that to 3 sig figs. Okay, so important to keep that in mind. Now, once you have this, 173 meters, then you can use with any of the equations. Now, I honestly, in order to find V final, I think it's just easier to use the equation we used in the previous problem, where it's A delta T plus V initial. And then that's just ends up being 2.4 times 12, which, you can, 12 times 2.4 and do that on the calculator. That gives you 28.8. And it was actually 12.0 and 2.40. So I didn't write down all the sig figs. You don't need to throw those into the calculator. The calculator doesn't care. Those are for reminders when you're rounding. And again, that means we get 3 sig figs. That's all we need. So we get 28.8 meters per second. Okay. Now, it's important to know that if you used 173, you would have done an intermediate rounding step. So be real careful if you use something you've calculated and then round it. Okay. It's better to avoid doing that. This would basically be sufficient for showing your work. Write down the equation, show that you've substituted in, and solve for the thing you're after at the end. All right. Okay. So I think I'll skip that one. All right, we'll do this one. Now this is a free fall problem. So calculate the height of a cliff. It takes 2.3 seconds for a rock to fall when it is thrown straight up from the cliff at an initial velocity of 8 meters per second. Okay, so we want to calculate the height. So this is what it's saying is, and we could use delta x for displacement, but a lot of times when it's vertical, you end up using delta y. Okay, now important that's just notation. You could just as easily use delta x, but it's a vertical displacement. So we don't know what that is. We want to find this. That's fine. Okay. And this is just part A. Now, the other thing it says is that delta t is equal to 2.35 seconds. Now, our initial velocity, this is important. Okay. Now it says 8 meters per second. Now we can do this. Now so 8.00 meters per second. Now, here's something that is implied if we write that. Basically, what we're saying is that down is positive because this thing, this object, or no, up is positive. Okay, so up is positive. Now, what this means is it means that that down will be negative. So anything directed downward, we need to give the negative sign. Okay. Now, we don't know what the final velocity is. That is, that's something we don't know. We don't care about at the moment. We might have to find that in some problem. But we do know the acceleration. And the acceleration is g, but it is negative g because it's down. Messing up these signs is a major way that that things can go wrong here. So it's negative g. It's g in the downward direction, which would be negative 9.81 meters per second squared. Now you'll notice this is it's a somewhat common to use 3 sig figs in these problems. A little hint, and I will tell you for the purposes of your free response in order to make this easier. What I will do, I will allow you to just use G equals 10. So you can use G equals 10. Okay. So here's the thing. G equals 10 is not super accurate in terms of calculation, but it makes the nitty-gritty of grinding through the algebra a lot faster, which is why I don't really care. What I want you to be able to demonstrate, and I'll do this with G equal 10, negative 10. Negative 10 point, we'll just say 10.0 for, well, I'll just leave it as negative 10. And then we'll just ignore the sig figs there because that's a rounded version. The point I'm getting at is, like I said, the calculations will go much more smoothly if G is equal to 10. And I'm not super concerned that you can't do the algebra if G was equal to 9.81. You probably can. It's just faster. And I want you to focus on being able to set up and solve these problems, not necessarily crank out these weird decimals. Okay, so G is equal to, I'm going to do this one with G is equal to negative 10 meters per second squared. Okay, so keep that in mind. All right, now basically what we want to do is we want to find our equation, and that's just going to be delta y is equal to 1/2 a delta t squared plus v sub I delta t. All right, so we find the delta y. It's going to be 1/2 times negative 10 times 2.35 squared plus 8 times 2.35. Okay, so going through this, what I'm going to get here is negative 26.6125, keeping all the decimals. I could go to like the third, that would be fine, and then round, but because I only need to keep 3 sig figs. So, but I'm just going to keep all of them. And then that would be 18.8. And then when I find this, I get delta y is equal to negative 7.81 meters. Okay. Now, what that means, it means that the height was 7.81 meters, but it means the object went down. Okay. So that's the idea, is that it went down 7.81 meters, and that's what the negative is telling us, and it makes sense that it would go down. Down being down being the way things fall. Okay. So for part B, it's asking the same thing again. So this time we actually know delta y, though. So we'll use negative 7.81 meters. And we don't know delta t. It's asking us to find a time. So that's what we're looking for. Now, the difference here is it says v sub I is still 8.00 meters per second, but it's thrown straight down, which means, again, like I said, we need to make this a negative. If it's going down, we need to make it a negative. Okay. And then our A is going to be negative 10 meters per second squared again. All right. So that's what we go with there. Now, again, we don't know V final, but we're basically going to be using the same equation that we did before. Now, this becomes a bit of, this can be a little bit, it can be a little bit frustrating because what we have here is we still have delta y equals negative or 1/2 a delta t squared plus v sub I delta t. And this is this ends up being a quadratic. So we'd have negative 7.81 is equal to 1/2 times negative 10 delta t squared minus 8 delta t. Okay, so rearranging, we're going to have 5 delta t squared, moving that over to the left, plus 8 delta t minus 7.81. Now, how you would go about doing this would be with the quadratic formula. So I would not even try to do this with factoring. So as a reminder, the quadratic formula is so delta t would be negative b plus or minus square root b squared minus 4ac all over 2a. So from there, we'd have negative 8 plus or minus 8 squared is 64 minus 4ac. That'd be 20, and it turns out to be a plus. So because it's negative 7.81. So 7.81 times 20 is 156.2. All over 2a would be 10. So we'll add 64 to that. Take the square root. And what we end up with here is we end up with negative 8 plus or minus 14.8 over 10. Now, here's the thing. Do we use the plus or the minus? Well, this is where you have to think about it physically. If we use the minus, we're going to end up with a negative time. And we can't have time be negative. We can only have time be positive. So we end up needing to go with the plus. So that's going to end up like 6, well, should be 8.4. Leave that 6.8 4 over 10, and that's just going to give us 0.684 seconds. Okay, so sometimes you do need to pull out this quadratic formula. That will happen if you have an equation with a square term to solve in it. It's much easier if your velocity term is 0, but they don't always give that to you. So you know, you gotta be careful with that. All right. So let's think I'll just do one more. Some of these are a bit much. Okay, so I'll grab this one. All right. So kangaroo can jump over an object 2.5 meter high. Calculate its vertical speed when it leaves the ground and calculate how long it's in the air. Okay. So what we'd want here is we want to define the things we have and the things we want. Okay. So the first thing we have is that the delta y is 2.5. Okay. Now 2.5 meters, 2.50 meters. Okay. Now, what about our initial velocity? Well, turns out we don't know this, but that is what we want. That's the speed it has when it leaves the ground. Okay. Now, another obvious one is that we know A is equal to negative G because I let Y be positive this time. And this time the kangaroo is going up. Okay, so I still want A to be negative, so that would just be negative 10 meters per second squared. Now, the last piece of this puzzle is a little tricky, and we don't know delta T. That's something we're looking for in part B. So there must be a way to get V final. And this is what happens when you have something in free fall when it reaches its maximum height. This is an important thing to remember. And the way you can say this, basically what we're going to assume is this is its max height. And the point is at maximum height, the object turns around. Okay. So as we saw, when an object turns around, that meant something about its velocity. And that was its velocity was equal to 0. So basically, at delta, when this thing reaches a height of 2.5 meters, its maximum height, gravity has basically slowed it down such that it is now going 0 meters per second. Okay. And again, sometimes these things can be a little tricky to figure out, but that is basically how you would need to do it. So From there, what we want to do is we wanted to find v sub I. So I think the easiest way to do that one is with I think this is the fourth equation, but it's v final squared equals v initial squared plus 2a delta. In this case, it'd be delta y, not delta x. But in any event, so v final was 0, and that's equal to v initial squared plus 2 times negative 10 times 2.5. Okay. And basically what we're going to have here, that is going to give us 50 equals v sub I squared. And from there, what we can do is we can could just take the square root. It's going to be a little over 7, but v sub I is then going to be 7.07 meters per second. And again, that is a little bit fudged because, again, I did use G for 10, but just as long as you know you're making an approximation there, it's not a bad approximation. It works. Okay. All right. Now, here's the thing about B. I misled you a little bit with B because it asks how long it's in the air. So the problem with this is that when it gets to the top, it's still in the air. It hasn't hit the ground again. Okay. And the issue is then it gets to the top, it's still in the air. It's got to come back down. All right. So that is kind of the problem with this. So we're not actually looking at the same situation. And that is key for some of these problems. You're not always looking at the same situation. So it turns out some of these things have actually changed. Now, good for us. We now know that for this new situation, our initial velocity is 7.07 meters per second. We still know A, that's just negative 10 meters per second squared. Now, the interesting thing is that we don't know what V final is anymore. Okay. It was 0 in the previous case, but as a reminder, as soon as it gets to the top, it's going to start falling back down and it's going to pick up speed. So we don't know what that is anymore. So you got to be real careful with that one. All right. Now, delta T is what we are asked to find, which means we should be able to get delta Y. Now, this is another one that can be kind of tricky. Okay. And the key here is that what you have here, if we, I'll try and draw a little stick figure kangaroo. Don't laugh at my stick figure kangaroo. But there's its tail, there's its little arms, and there's its little head. Okay, fine. Now, what the kangaroo is doing, and I'm not gonna draw this right on top. I'm gonna draw it kind of off to the side, but it's jumping up and then back down. Now, if we might say it goes a little bit forward, but we're talking about its vertical displacement here. Now it goes up and then back down to where it started. This is what's really cool. It's back where it started. As a reminder, anything that ends up back where it started has a very simple displacement to calculate. It's just 0. Okay. Now, if we're going to find this, what we're going to need is the equation we'll want to use is the delta y, because we have delta y, 1/2 a, we have a delta t squared, that's what we're looking for, plus v sub I delta t. Now, unfortunately, this is another one where you have a delta t squared. But turns out this one's a little nicer to solve because when we plug in, we get 0 equals 1/2 and then negative 10 delta t squared plus 7.07 delta t. Now that's going to give us negative 5 delta t squared plus 7.07 delta t. Now, if you remember from algebra, this is actually factorable. You can factor out a delta t. Negative 5 delta t plus 7.07. And then what you can do is you can set these two factors equal to 0 because they're both equal to 0. So delta t equals 0. So this corresponds to the start. So this is before the kangaroo is jumped. And that's why, at a time of 0, poor kangaroo has jumped. At a time of 0, you have a displacement of 0. That makes perfect sense why that would be the case. But the second one, when negative 5 delta t squared plus 7.07 equals 0, this is when the kangaroo lands. All right. So it will have a displacement of 0 at 2 different points in its path. That's why there are 2 solutions for this. Okay. So that's one of the things that is happening here. It's actually a plus, not a minus. And when you solve for this, and it's not squared, it's just delta t, you get delta t equals 7.07 over 5. We can go ahead and divide by 5, and we end up with delta t equals 1.41 seconds. All right, and that would be it. Okay, so I'm going to go ahead and end this lecture here. But hopefully you found these examples useful. Hopefully you can work through the homework a little bit better now. Thank you for joining me today, and I will see you next lecture.